Hello everyone. In this class, we will discuss about continuous charge distribution. Okay. The charge of an electron is very small. The charge of an electron or protons are very small. But in practice, in reality, we deal with the charges which is very much greater than the charge of an electron or proton. Okay. Suppose a bulb, this is a bulb, okay, and this is a conducting wire and this is the switch, okay. So the bulb will only glow when the electrons or the charged particle will flow through this conducting wire, okay. Bulb कब glow करेगा? When the charged particles, electrons are flowing through this conducting wire, okay. When the switch is closed, जब ये स्विच क्लोज होगा, यानी when you close the switch, what happens? Suppose this is a battery, the electron will flow through this conducting wire. यहाँ इलेक्ट्रॉन कैसे फ्लो करेगा? The electron will flow through this conducting wire. The electron will continuously flowing through this conducting wire, for which the bulb will continuously glow. यहाँ ये जो conducting wire है, through this conducting wire, the electrons are continuously flowing. There is no break between two charges. There is no break between two charges. That is why ये जो bulb है, it will be glowing continuously. अगर दो charges के बीच में कोई gap होता, suppose this is a point charge and this is another point charge. These are the 2 point charges. Okay, then what happens? Suppose when this charge will flow through this conducting wire, the bulb will glow. In between the gap of two charged particles, in between the gap of two charged particles, the bulb will not glow. ऐसा तो नहीं होता. जब हम स्विच ऑन करते हैं तो क्या होता है? बल्ब इज कॉन्टिन्यूअसली ग्लो करता है. बल्ब क्या होता है? कॉन्टिन्यूअसली ग्लो करता है. दैट मीन्स अगर बल्ब कॉन्टिन्यूअसली ग्लो करता है तो ये जो कंडक्टिंग वायर है, थ्रू दिस कंडक्टिंग वायर चार्ज भी क्या होगा? कॉन्टिन्यूअसली ग्लो करेगा, यानी कॉन्टिन्यूअसली फ्लो करेगा. When charges are flowing continuously through this conducting wire, then the bulb will also glowing continuously. अभी देख रहे हो ये जो bulb है, it is glowing continuously because the charges through the conducting wire is flowing continuously. Okay, that means this is a conducting wire. ये हमारा एक conducting wire है. Okay, through this conducting wire the charges are flowing continuously. ये जो conducting wire है, यहाँ क्या हो रहा है? The charges are flowing continuously. यानी यहाँ पर कोई point charge का concept नहीं है, या ऐसा ये point charge, ये point charge, ये ऐसा नहीं है. इसमें क्या है? ये जो straight line है, यही एक चार्ज बोल सकते हो. स्ट्रेट लाइन इज ऑल्सो द कॉम्बिनेशन ऑफ लार्ज नंबर ऑफ पॉइंट्स. ओके, सो अगर मैंने एक स्ट्रेट लाइन बनाया है तो इसमें तो कोई एक पॉइंट नहीं दिखाई देगा ना, सब पॉइंट्स मैंने जुड़ के ये स्ट्रेट लाइन बनाया है. दैट मीन्स चार्ज भी ऐसा ही. यहाँ पर क्या होता है? द चार्जेस आर यूनिफॉर्मली डिस्ट्रीब्यूटेड ऑन दिस लाइन. द चार्जेस आर यूनिफॉर्मली और continuously distributed on that line. There is no break between two charges. Okay, there is no break between two charges. Charges are continuously distributed on a line. Sometimes the charges are continuously distributed on surface. When charges are continuously distributed on surface, then it is known as surface charge distribution. And sometimes the charges are uniformly distributed on a 3-dimensional body cube. Here also the charges are continuously distributed inside the cube. This is known as the volume charge distribution, which is known as the volume charge distribution. Okay, so we can see that the charge which we deal with in reality is much greater than the charge of an electron. ओके, जो ये जो एक कंडक्टिंग वायर है, थ्रू दिस कंडक्टिंग वायर द चार्जेस आर कंटिन्यूअसली फ्लो करता है. कोई ऐसा एक चार्ज गया उसके बाद दूसरा गया, ऐसा नहीं है। द चार्जेस आर कॉन्टिन्यूअसली फ्लोइंग, यानी इफ दीज आर द कॉन्टिन्यूअसली फ्लो ऑफ चार्ज, इसमें कोई ब्रेक नहीं मिलता। यानी ऐसा नहीं है ये एक पॉइंट चार्ज Q1 है, दूसरा Q2 है, तीसरा Q3 है, इसमें देखो ब्रेक है, ऐसा नहीं होता। द चार्जेस आर जेनरली कॉन्टिन्यूअसली डिस्ट्रीब्यूटेड। अगर कॉन्टिन्यूअसली ऐसे डिस्ट्रीब्यूट होगा तो उसका मैग्नीट्यूड बहुत बड़ा होगा। दैट इज वाई मैंने कहा है द चार्जेस विच वी डील इन रियलिटी इज मच ग्रेटर देन द चार्ज ऑफ एन इलेक्ट्रॉन। ओके, सो लेट अस डिस्कस द टॉपिक द लाइन चार्ज डिस्ट्रीब्यूशन। ओके, पहले हम डिस्कस करेंगे द लाइन चार्ज डिस्ट्रीब्यूशन। लाइन चार्ज डिस्ट्रीब्यूशन, line charge distribution. The line charge distribution is denoted by lambda also. It is denoted by lambda. So what is line charge distribution? If the charges are distributed on a line or on a conducting wire, then it is known as the line charge distribution. Suppose this is a line, or you can say this is a conducting wire. On this conducting, or if charges are distributed, if charges are uniformly distributed, then this is known as the line charge distribution. That means the line charge distribution means the charges are distributed on a line or on a conducting wire. Okay, then there is another term, line charge density. Line charge density is denoted by lambda. Line charge density, which is denoted by lambda. So what is line charge density? Line charge density means the line charge density at any point on a line is the number of charge contained per unit length at that point. Okay, so what is line charge density? Line charge density at a point on a line is the number of charge contained per unit length at that point. Okay, so what is this lambda? It is line charge density is the number of charge per unit length at that point, number of charge per unit length at that point. Okay, or it is denoted by lambda. Lambda is equal to your Q by L. Lambda is the line charge density, which is the number of charge contained per unit length. What is SI unit of lambda? SI unit of lambda is coulomb per meter. Coulomb per meter. Okay, it is coulomb per meter. Suppose if we have a ring, okay, if we have a ring of radius r, जिसका radius क्या है, capital R, and the q charges are distributed uniformly over the ring. Q charges are distributed over the ring uniformly. The Q charges are distributed over the ring uniformly. Then the line charge density lambda will be equal to charge divided by circumference of the ring, or you can say length of the ring, which will be equal to twice pi r. Okay, if Q charges are uniformly distributed over the ring of radius r, then the line charge density of the ring will be Q divided by circumference. Q means total charge of the ring and twice pi is the circumference of the ring. Okay, what is the SI unit of this line charge density? SI unit is equal to your coulomb per meter. Okay, here in this diagram you can see on this line, this is a line and the charges are uniformly distributed on this line. Charges are uniformly distributed on this line. Okay, for this line charge distribution we are going to calculate the electric field at point P. Okay, for this uniform line charge distribution, we are going to calculate the value of electric field at point P. ये जो line है, upon this line the charges are uniformly distributed, okay, and because of that charges we are going to calculate electric field it at this point. ओके, लाइन चार्ज डिस्ट्रीब्यूशन मीन्स क्या, ये जो लाइन पर चार्जेस आर यूनिफॉर्मली डिस्ट्रीब्यूटेड, इसमें कोई ब्रेक नहीं है, द चार्जेस आर कॉन्टिन्यूअसली डिस्ट्रीब्यूटेड ऑन दिस लाइन. ओके, हम क्या करेंगे, पी पॉइंट में इलेक्ट्रिक फील्ड निकालेंगे. क्या निकालेंगे, इलेक्ट्रिक फील्ड निकालेंगे. वी आर गोइंग टू कैलकुलेट इलेक्ट्रिक फील्ड एट पॉइंट पी. अगर इलेक्ट्रिक फील्ड निकालना है पी पॉइंट में, फॉर दैट वी हैव टू कंसीडर ए टेस्ट चार्ज. हमको क्या लेना पड़ेगा, पी पॉइंट में एक टेस्ट चार्ज क्यू नॉट लेना पड़ेगा. ओके, देन यू कंसीडर ए वेरी स्मॉल लेंथ एलिमेंट डीएल. देन यू कंसीडर ए वेरी स्मॉल लेंथ एलिमेंट डीएल. इसके बाद हमने क्या किया, we have considered a very small length element dl. Okay, here d is used to represent small. We have considered a very small length element dl. Okay, on that length dl, what is the number of charge? Can you say the number of charge? The number of charge contained on length, number of charge contained in length dl is dq, which will be equal to lambda into dl. We have considered a very small length, that is why the charge will be small. We have considered a very small length dl, that is why the charge will be very small. That is why we have written dq. Okay, dq is what, the number of charge contained in the very small length dl, and the amount is how much, lambda into dl. इसमें जो lambda है वो क्या है, lambda is the number of charge contained per unit length. Okay, lambda is what, it is the number of charge contained per unit length. और हमने कितना लेंथ लिया है, we have choose dl length. That is why the charge contained in length dl will be how much, it will be your lambda into dl. Okay, here we have considered a length of dl, and on that length the amount of charge is how much, the amount of charge is dq. Okay, and that dq charge will repel this q naught in this direction. ये जो dq charge है, the dq charge will repel this q naught in this direction with a force F(L). Okay, L for line charge distribution. Okay, if the point P is at a distance r, then the force exerted upon that point charge due to this length, due to this small charge dq will be how much, Fl will be equal to your 1 by 4 pi epsilon naught dq q naught by r square r cap. Okay, here this is what, from Coulomb's law, this is the force acting upon a test charge q naught due to a small element of charge dq. Okay, this is the force acting on a charge q naught due to a very small length element of charge dq. Okay, then what will be the value of electric field at that point? Value of electric field at that point, EL. Here we am writing L because L represents the line charge distribution. The electric field at that point due to this small charge dq will be equal to your Fl divided by q naught. Okay, that means if you divide this by q naught, then the electric field at point P due to a very small length element dl, due to a very small charge dq will be equal to what, 1 by 4 pi epsilon naught dq by r square r cap. So this is what, this is the electric field at point P due to a small charge dq at point P. P पॉइंट में ये इलेक्ट्रिक फील्ड का वैल्यू है फॉर ए वेरी स्मॉल चार्ज dq. ओके, बट हमको क्या निकालना है, वी नीड टू कैलकुलेट द इलेक्ट्रिक फील्ड एट पॉइंट P ड्यू टू द होल लाइन चार्ज. Okay, we need to calculate the electric field due to the whole line charge, but we are calculating the electric field at point P due to a small amount of charge dq. We are only calculating the electric field at point P for a small amount of charge dq which is present in the length dl. dl length में जो चार्ज है dq, उसी के कारण हमने P पॉइंट में इलेक्ट्रिक फील्ड निकाला है. हमको अभी क्या निकालना है? हमको अभी निकालना है द टोटल इलेक्ट्रिक फील्ड एट पॉइंट P ड्यू टू द एंटायर लाइन. ओके, ये जो इलेक्ट्रिक फील्ड भी होगा ये भी वेरी स्मॉल होगा. ओके, इलेक्ट्रिक फील्ड, और ये फोर्स भी क्या होगा? वेरी स्मॉल होगा, क्योंकि वी हैव कंसीडर्ड अ वेरी स्मॉल अमाउंट ऑफ चार्ज. दैट इज व्हाई वी हैव कंसीडर्ड अ वेरी स्मॉल अमाउंट ऑफ चार्ज. दैट इज व्हाई द फोर्स ऑफ रिपल्शन विल बी वेरी स्मॉल. स्मॉल रिप्रेजेंट करने के लिए हमने ये डी लिखा है. ओके, DFL, दैट मीन्स the force will be very small. The force upon test charge will be very small because we have considered a small amount of charge. We have considered a small length. In small length, the small charge will be there. Okay, and the electric field due to the small element of charge will be this one. Okay, the total electric field. Therefore, the net electric field at point P due to the line charge is, okay, what will be the total electric field due to this line charge? The total electric field EL will be equal to your integration DEL. Okay, तो ये जो DEL है, this is the electric field for a very small length element और for a very small amount of charge dq. हमको क्या निकालना है? इलेक्ट्रिक फील्ड निकालना है ड्यू टू दिस एंटायर लाइन. पूरा लाइन के लिए यहाँ पर हमको इलेक्ट्रिक फील्ड निकालना है. उसके लिए हमको क्या करना पड़ेगा? फॉर दैट वी नीड टू डू द इंटीग्रेशन. अगर होल लाइन के लिए P पॉइंट में इलेक्ट्रिक फील्ड निकालना है तो उसके लिए हमको क्या करना पड़ेगा? इंटीग्रेशन करना पड़ेगा. इंटीग्रेशन EDEL. ओके, अगर इंटीग्रेट करोगे तो इसमें ये जो 4 पाई एप्सिलॉन है 1/4 पाई एप्सिलॉन नॉट, हाँ, ये तो कांस्टेंट, ये बाहर आ जाएगा. इन प्लेस ऑफ dq what we can write? It will be your lambda dl by r square r cap. ओके, यहाँ पर भी हम लिख पाएंगे EL, इलेक्ट्रिक फील्ड एट पॉइंट P ड्यू टू द entire line charge will be equal to lambda is also constant. Lambda is what? The number of charge per unit length. Okay, that is why lambda is also constant. But here that r is different. R means what? The distance to the point P from any part of this line. That is why here r is variable, but lambda is constant. That is why we can take lambda divided by 4 pi epsilon naught integration dl by r square r cap. So this is what? This is the value of electric field at any point P due to a line charge distribution. Okay, then we will discuss the surface charge distribution. So line charge distribution is very simple. I am again repeating it. What is line charge distribution? मैंने क्या कहा है? हम ये जो charge है which will deal in reality, it is very much greater than the charge of an electron. ये जो charges are continuously distributed on a line or on a conducting wire for which the bulbs are glowing. ये जो bulb glow कर रहा है, fan चल रहा है, continuously the motor is rotating और continuously the bulb is glowing because the charges are continuously flowing, or you can say the current is continuously flowing. करंट continuously flow हो रहा है, इसलिए बल्ब जो है continuously glow कर रहा है. बल्ब continuously इसलिए glow कर रहा है क्योंकि current is continuously flowing, और current इसलिए continuously flow हो रहा है क्योंकि charges are continuously flowing. That means between two charges there is no break, कोई break नहीं होता. Okay, the charges are continuously flowing. Okay, if it is flowing on a line, suppose we have considered a line or a conducting wire. On this line the charges are uniformly distributed like this. Okay, and here we define a term, line charge density. What is line charge density? Line charge density means the number of charge contained per unit length at a point on the line. Okay, here it is denoted by lambda. Lambda is the number of charge per unit length. तो SI will be coulomb per meter. उसके बाद हमने क्या कहा? ये जो लाइन चार्ज है here charges are uniformly distributed, and due to this line charge we are going to calculate the electric field at point P. ओके उसके लिए हमने क्या किया, वी हैव कंसीडर्ड ए वेरी स्मॉल लेंथ dl. ओके उसी लेंथ में कितना चार्ज होगा, द चार्ज कंटेन ऑन दैट लेंथ dq will be equal to your lambda into dl. यानी we have considered a very small length dl, on that length कितना चार्ज होगा, the charge will be dq which is equal to lambda into dl. okay, and that charge dq will repel q naught. हमको एक्चुअली p पॉइंट में इलेक्ट्रिक फील्ड जो निकालना है, इसलिए हमने क्या किया, we have taken a test charge q naught, and this charge dq will repel this q naught in this direction with a force dfl. okay, and according to Coulomb's law the force will be how much, 1 by 4 pi epsilon naught dq q naught by r square r cap. and electric field at that point due to the small charge element, electric field क्या होगा, del will be equal to your fl by q naught होगा. If we simplify, that means we will find the electric field at point P due to a very small element of charge dq. ये जो electric field है, this is for a very small element of charge dq. बट हमको क्या निकालना है, ड्यू टू द एंटायर लाइन चार्ज, पूरा लाइन चार्ज के लिए P पॉइंट में इलेक्ट्रिक फील्ड निकालना है. इसलिए हमने क्या किया, हमने इंटीग्रेट किया. इफ वी इंटीग्रेट देन वी कैन फाइंड द इलेक्ट्रिक फील्ड एट पॉइंट P ड्यू टू द एंटायर लाइन चार्ज, एंड दिस इज द रिजल्ट. Okay, this is the electric field at any point P due to a line charge distribution, due to a line charge distribution. Okay, and sometimes the charges are distributed on surface also, so we will discuss the surface charge distribution. We will discuss the surface charge distribution. Surface charge distribution or surface charge density, which is denoted by sigma. What is surface charge distributions? We have considered a surface like this. We have considered this surface. If charges are uniformly distributed over the surface, okay, if the charges are uniformly distributed over this surface. तो यहाँ पर मैंने तो पॉइंट चार्ज बनाया है, ओके, बट ऐसा भी नहीं है. ये जो इसमें जो ये जो व्हाइट बोर्ड है, इसमें तो ये जो व्हाइट वाला सेक्शन है, इसमें देखो एवरीथिंग इनसाइड दिस सर्कल एवरीथिंग इज व्हाइट. इफ यू कंसीडर व्हाइट एज ए चार्ज, तो इसमें देखो सब में व्हाइट है ना, तो यानी ये सब चार्ज है. सपोज ये सब क्या है, चार्ज है. द चार्जेस आर कॉन्टिन्यूअसली डिस्ट्रीब्यूटेड. यहाँ पर मैंने तो ऐसे कॉन्टिन्यूअसली नहीं बना सकता ना, इसलिए मैंने पॉइंट चार्ज दिखाया है. ओके, ये सब पॉइंट है, बट हियर द चार्जेस आर कॉन्टिन्यूअसली, पूरा कॉन्टिन्यूअसली डिस्ट्रीब्यूटेड. ऐसा कोई पॉइंट नहीं है, इट इज कॉन्टिन्यूअसली डिस्ट्रीब्यूटेड ऑन द सरफेस. इसमें यूनिफॉर्मली डिस्ट्रीब्यूट हो रहा है ओवर दिस सरफेस. ओके, तो व्हेन द चार्जेस आर यूनिफॉर्मली डिस्ट्रीब्यूटेड ओवर ए सरफेस, then it will be surface charge distribution. Okay, here also we define a term, surface charge density, which is denoted by sigma. So what is surface charge density? Surface charge density at any point on the surface is the number of charge contained per unit area. It is what? It is the number of charge contained per unit area. It is denoted by the letter sigma. Sigma is what? It is the number of charge contained per unit area. Sigma is equal to dq by ds. ds is suppose small area. Okay, suppose if we consider a small area element ds, suppose we have considered a small area element ds. Okay, and the charge contained on that surface ds will be how much? The charge contained on that surface ds will be equal to your sigma into ds. Okay, sigma into ds. Okay, what is the SI unit of this surface charge density? SI unit of sigma is Coulomb per meter square. And what will be the dimension of sigma? dimension of sigma will be equal to your dimension of charge by dimension of area. Dimension of charge is A into T and dimension of area is equal to your L square. So dimension will be equal L to the power minus 2AT. This is the dimension of surface charge density. So what is surface charge density? Number of charge contained per unit, number of charge contained per unit area, per unit area. Okay. Now suppose this is our surface. I am again redrawing the diagram. Suppose this is a surface, this is a surface. Upon this surface the charges are suppose uniformly distributed. The charges are uniformly distributed like this. Okay. And due to this surface charge distributions, we need to calculate electric field at point P. P point पर हमको क्या निकालना है? Electric field जो निकालना है. Okay, due to this surface charge distribution, we are going to calculate electric field at point P. For this, यहाँ पर P point पर electric field निकालना है, इसलिए हम क्या करेंगे? At point P, we have taken a test charge Q naught. We have taken a test charge Q naught. Okay, and we also consider a small area element. This is a small area element ds. This is what? This is a small area element ds, and the charge contained on that small area element will be how much? Charge contained on the small area element ds is dq will be equal to your sigma into ds. What is dq? dq is the amount of charge contained on the small area element ds. ये जो ds area element है इसमें कितना charge है? dq amount of charge is there, and the dq is equal to how much? Sigma into ds. Okay, here also the point P is at a distance r from dq. ये जो ds एरिया एलिमेंट है इसमें कितना चार्ज है? इसमें dq amount of charge is there. How much charge is there? dq amount of charge is there, and dq charge will repel q naught in this direction. This dq amount of charge will repel q naught in this direction with a force dfs. This dq amount of charge will repel q naught in this direction with a force dfs. Okay, the charge is very small because we have considered a small area element. As the charge is small, the force exerted upon q naught will be also small. That is why we have written dfs. dfs means force exerted upon a test charge q naught due to the surface charge distribution, as for surface charge distribution, and therefore the force will be very small because we have considered a very small element of charge. To represent small, we have written this letter D. Okay, and what is the dfs? It will be equal to, according to Coulomb's law, it will be 1 by 4 pi epsilon naught dq q naught by r square r cap. dq q naught by r square r cap. Okay, this is the force exerted upon a test charge q naught due to a small amount of charge dq which is present in a small area element ds. Okay, then what is the value of electric field? Electric field at point P will be des, means electric field at point P due to surface charge distribution, and the value of electric will be very small because we have considered a small amount of charge dq. Okay, des will be equal to your dfs divided by q naught, which will be equal to your des will be equal to, if you divide this dfs by q naught, it will be equal to your 1 by 4 pi epsilon naught dq by r square r cap. dq by r square r cap. So this is the value of electric field at point P due to a small charge dq present in a small area element ds. But we are going to calculate the electric field at point P due to this entire surface charge distribution. Okay, due to this entire surface, the electric field at point P due to the entire surface क्या होगा? Therefore, the electric field due to entire surface is ES. एंटायर सरफेस के लिए P पॉइंट में इलेक्ट्रिक फील्ड जो होगा वो होगा ES. इलेक्ट्रिक फील्ड ड्यू टू एंटायर सरफेस डिस्ट्रीब्यूशन which will be equal to integration DES, which will be equal to integration DES. Okay, if we integrate DES, then we will find the electric field at point P due to the surface charge distribution, which will be what is DES here? DES means 1 by 4 pi epsilon naught dq by r square r cap. Okay, so here we can write 1 by 4 pi epsilon naught. In place of dq we can write sigma into ds r square r cap. Okay, therefore electric field at point P due to the entire surface charge distribution ES is equal to sigma is what? The surface charge distribution. Okay, surface charge distribution, number of charge per area, which will be constant. So it will be sigma divided by 4 pi epsilon naught integration ds by r square r cap. Sigma by 4 pi epsilon naught integration ds by r square r cap. Okay, this is the electric field at point P due to a surface charge distribution. Okay, and then we will discuss the volume charge distribution. So volume charge distribution is the charge contained on a three-dimensional body like a cube. Suppose this is a cube, this is a cube, and inside the cube, suppose the charges are uniformly distributed. Suppose the charges are uniformly distributed like this. So okay, this room can be considered as a cube, and inside the cube the charges are uniformly distributed. Suppose the air, if you consider the air as a charge, the air are uniformly distributed inside the room. Okay, if you consider the air molecule as some charges, then the charges are uniformly distributed. Okay, over this room. Suppose these are the charges which are uniformly distributed over this volume. Okay, then the term volume charge density, which is denoted by the rho, which is denoted by the letter rho. What is volume charge density? Volume charge density means volume charge density is the amount of charge contained per unit volume at any point inside the cube. Okay, so what is volume charge density? Volume charge density at any point inside the volume is the number of charge contained per unit volume. That means rho is what? The amount of charge contained per unit volume, dq by dv. Therefore dq will be how much? dq will be rho into dv. dq is the amount of charge contained in a small volume element dv. Okay, here the SI unit of rho or volume charge density, SI unit of rho is coulomb per meter cube. Okay, and what will be the dimension of rho? It will be your coulomb, dimension of coulomb is 80 and is L cube, L to the power minus 3, 80. Okay, now you are going to calculate the electric field at this point P due to this volume charge distribution. So here we are going to calculate electric field at point P. Okay, for this we have to consider a test charge at point P. We know that electric field means the force acting upon a test charge. So we have considered a test charge. Okay, for this we have to consider a small volume element. Okay, we have to consider a small volume element. Suppose this is a small volume element. Inside the cube. okay, and the volume is suppose dV. The volume is suppose dV, and the charge contained inside the volume dV will be equal to your charge contained inside the volume element dV is dq is equal to rho dV. dq is equal to rho dV, and so inside the volume element dV, the amount of charge is how much? It will be dq. dq is the amount of charge present inside this volume, and that dq charge will repel this q naught. Okay, if this is the point P, okay, this dq charge will repel q naught in this direction, okay, with a force dfv, and that according to Coulomb's law, dfv is equal to 1 by 4 pi epsilon naught dq q naught by r square r cap, okay, r square r cap. And the electric field at the point will be, due to this small charge element dq, electric field at that point due to the small charge dq will be equal to your dfv divided by q naught, which will be equal to your 1 by 4 pi epsilon naught dq by r square r cap. This is the value of electric field at point P due to a small charge element dq, okay, small charge element dq. Therefore total electric field at point P due to volume charge distribution is EV is equal to integration dEV, okay. The total electric field due to the entire volume will be equal to integration dEV, which will be equal to your dEV means what? 1 by 4 pi epsilon naught dq by r square r cap, okay, or it will be EV 1 by 4 pi epsilon naught integration dq by r square r cap. dq means, in place of dq what we can write? You can write rho dV, okay, rho dV. Here rho is constant, that is why it will comes out rho by 4 pi epsilon naught integration dV by r square r cap. So this is the value of electric field at point P due to a volume charge distribution, okay. So if you have any doubt, you can call me also, okay. Any question if you have, then you can call me, then I will solve that problem, okay. In next class we will discuss about the electric flux and area vector, okay. In next class we will discuss about the electric flux and area vector.